Phase diagrams. So a phase diagram is where we show pressure on the y-axis, temperature on the x-axis, and we are mapping the phase of the substance, the state, physical state. So we've got different regions that represent conditions under which that particular phase is stable. And separating the regions, we have lines or curved lines that represent a set of temperatures and pressures where the substance is in equilibrium between the two states. So we have a vaporization curve showing where the gas and the liquid are in equilibrium, a sublimation curve where the solid and the gas are going back and forth, and a fusion curve where melting and freezing occurs. For many substances, those three curves meet in a single point, and that's called the triple point. And that's a unique set of conditions in which you can have all three states in equilibrium with each other. You can have a liquid, a solid, and a gas of the same substance all at the same time. That's another kind of trippy thing. Okay, so here's a phase diagram for water. And these are not to scale, so it's just, qualitative here. So as pressure increases going up and temperature increases going to the right. So this dashed line represents atmospheric pressure. Here we have 0 degrees Celsius, which is the freezing point of water, and 100 degrees Celsius, which is the boiling point of water. So if we find where atmospheric pressure and 100 degrees Celsius intersects, it is on this line, which is separating liquid water from gas. So this is where water would be boiling. If you increase the pressure, to get to that boiling point, you have to increase the temperature. If you decrease the pressure, then the water will boil at a lower temperature. Over here, this is the freezing point of water at 0 degrees Celsius and 760 torr. Water's a little bit weird in many ways. If you put pressure on water, it will melt at a lower temperature. And that's part of what makes ice so slippery. Do you ever wonder how ice skates work? It's not just that you've got this very slim blade that you're putting all your weight on. When you put all your weight on that thin blade of the skate, it puts a lot of pressure on the water and actually causes the water to melt a little bit. So if you increase the pressure, the melting point of the ice is lowered. And so you can glide so nicely on ice skates because it causes the top layer of the ice to melt, which makes it much slipperier than if it was just ice without any liquid layer on it. So this is the fusion curve where you've got the transition between solid and liquid. This is the sublimation curve where you've got solid to gas transitions.
So it's not just a transfer of enthalpy then that melt the ice, or is it also just pressure itself?
Well, the freezing point of water is dependent on pressure. It's not a strong dependence. The slope of this line is almost vertical. If it was vertical, there'd be no temperature dependence. But we'll see that other substances have different slopes. This is a negative slope. Other substances have positive slopes, whereas where you increase the pressure and it actually freezes at a higher temperature. So this is the triple point. If you achieve this temperature at this pressure, you can have all three states of water existing together. This is the critical point. Above this temperature, the line ends because above that temperature, you can't have a liquid. And so the gas and the liquid there's no dividing between them. It's a supercritical fluid.
What is supercritical fluid of water used for? What do you use?
Well, supercritical H2O would be, it happens at such a high pressure and temperature that it's not all that useful for anything. That's why they use, CO2 to decaffeinate coffee. So let's see. I think this is zoomed in on water. So what do you need to be able to do with these phase diagrams? You need to be able to identify the different regions, solid, liquid, and gas. And you can do that by knowing that the gas will exist at a higher temperature than the liquid, and the liquid at a higher temperature than the solid. So we can do what's called navigation in this phase diagram. So if you take 1 atmosphere of pressure and you just start here and you move across, we see here we've got solid water, we've got ice, and as we increase the temperature at the same pressure, we come to the fusion line where the ice is going to melt, and we can look down here and see what the temperature is there. And then as we continue to increase the temperature, the water's going to warm up until we get here, and then it's going to boil, and then we're going to have the gas state of water after that. You can also go up and down looking at differences in pressure. So here at room temperature, if you decrease the pressure, you can actually cause the water to go into the gas state when you get down to this lower pressure. And so you can go, without changing the temperature, you can change the state. And that's how the ice skates work, is you increase the pressure and you can cause the water to melt. Here we've got iodine and carbon dioxide. So we talked about carbon dioxide, and here's the critical point for carbon dioxide is down here around 31 degrees Celsius, much lower than for water. Now, for both of these, for iodine and for carbon dioxide, this fusion line bends to the right. It's got a positive slope, whereas for water, it had a negative slope. Water's unusual in that way. And so we can find the triple point for these things, a critical point. Interesting thing for CO2, this is 72 atmospheres. The triple point here is at 5 atmospheres. That is crazy high pressure. The liquid state of carbon dioxide only exists at pressures of 5.1 atmospheres or higher. You cannot get liquid CO2 at atmospheric pressure. It just doesn't happen. And that's why at atmospheric pressure, we only see sublimation. We see it go directly from the solid to the gas state.
You said going down in below water level, 10 meters is 1 atmosphere or something like that.
Yeah. Mm-hmm.
How does a pressure cooker take all that?
Well, a pressure cooker and thinking about going below sea level or going below the surface of the water, I can't really reconcile those two ideas.